Bismillahirrahmanirrahim. So today we'll be dealing with the introduction of spectroscopy. Since our this course is, the examination pattern in this course is objective type, so I'll not be going deep into this. So I'll just trying to complete this course as per the need of the examination. Now, other important things, since at the BSc level, the spectroscopy is not that much exposed, so it's an elementary level here. So, and you people might not have read this, so I will try to make the things clear and get the concepts clear. So we can start here. In introduction to the spectroscopy, it is important first to know the spectroscopy. So it's clear here. So spectroscopy, as the word mentioned here, it is something, the word called spectra. The word spectrum is spectra here, so that means it has something to do with the light. So this branch actually deals with the light. Fine. So what actually it means? It means that the interaction of, so this branch deals with the interaction of electromagnetic radiation with the matter. So it can be solid, liquid, gas, or whatever matter exists in the universe. So interaction of the electromagnetic radiations, light, interaction of light with the matter. So what this interaction actually does, so it results in the transition in the molecules. It results in the transition in the atoms and molecules. Now this transition can be any type of transition. It can be between the electronic energy levels. So this transition can be between the nuclear energy levels. So this transition can be between the vibrational energy levels. So the transition can be between the rotational energy levels, and so on. We'll deal with this later. So the spectroscopy, basically we say it's the interaction of electromagnetic radiation in the matter, and then it leads to the transitions in the molecules and atoms. So what actually this ultimately does, it gives us the atomic and molecular structure. You can see here. So it finally results, this phenomena, it provides us the atomic and molecular structure. And the whole instrumentation which deals with this spectroscopy, so that's called as spectrophotometer, or we can use spectrophotometers also. So this is the basics. So it's basically the branch of science that deals with the interaction of electromagnetic radiation in the matter, and then it leads to the transition in the molecules and atoms, and it finally uses the atomic and molecular structure. And so the instrument which deals with this, they can be called as the spectrophotometers. Fine. Now this is the basics of the spectroscopy. So maybe the question may be asked from this. So that means, so what we now here know, that the important component of the spectroscopy is the electromagnetic radiation. So we'll go to the electromagnetic radiation. Electromagnetic radiation. So we'll start with the basics, that's the electromagnetic radiation. Just rub it. So start with the electromagnetic radiation. Electromagnetic radiation. Electromagnetic radiation. So electromagnetic radiation, so what do we mean by this electromagnetic radiation? So we know that it has an electronic and a magnetic component. So the radiations which we receive from the sun, so we have an electric component and we have a magnetic component. So electromagnetic radiation is basically, it possesses an electric component and a magnetic component, and those components, they are perpendicular to each other, and they are also perpendicular to the direction of propagation of the radiation. Fine. So we'll explain this electromagnetic radiation in two concepts. One is the wave theory. Of electromagnetic radiation, wave theory. So as per wave theory, the electromagnetic radiation, no, it's perfectly a wave. I'll show it here. It's like this, and so on. So it's like a wave. Let's start a starting point. So as per the wave theory, the electromagnetic waves, they have a wave character. So they have wave character. They travel in the space, the speed of light. They travel in the space with a speed, and the speed which is we know, c, 3 into 10 to the power 8 meter per second. 8 meter per second. So they travel in the light. So they travel in the space through a velocity which is equal to 3 into 10 to the power 8 meter per second. So as per wave theory, the electromagnetic waves, they have this, this ups and downs. We call it crusts and troughs. This is called crust, and then below this line is called as a trough. So they're the crusts and troughs. And then this wave travels, through the space. So this wave has the electric and magnetic components perpendicular to each other like this. It's electric component, this is magnetic component. If it is electric component, this is magnetic component. So electric and magnetic component. So this is the direction of propagation. Electric component, magnetic component. So this basically, it is basically this on the perpendicular here like this. That makes an angle of 90. So this is the electromagnetic radiation, that where we have electric and magnetic components, oscillating electric and magnetic components perpendicular to each other and perpendicular to the direction of propagation. Fine. So as per the wave theory, the electromagnetic radiations, they have oscillating electric and magnetic components perpendicular to each other and to the direction of propagation with a speed equal to the velocity of light. So now we can see here, we'll go back here. So this is a typical wave. So now this point you can select from this here, from this is called the amplitude of the wave, this one. So likewise this is the same as this. This is the amplitude of the wave, this one. So we called it A. Maximum displacement from this point, this is called extreme positions, is called as amplitude of the wave. Same is the case here, it's called amplitude of the wave. So now this distance between the two, maxima, is called maxima also. So this is called as a wavelength of the wave, lambda. So this is called as the wavelength. So between the two crusts is called a wavelength, or we can keep it in the two troughs also. Same is the case here. This is also called a wavelength. So that can also called a wavelength. And same is the case, we can use the wavelength from this point to this point. So this is the wavelength of the wave. This is the amplitude, the maximum displacement from the mean position to this. So these are the basic parameters in this wave. And they can be correlated as this, the frequency of the wave. That can be correlated like this. Nu is equal to c by lambda. So the frequency of the wave, and so that's called the velocity of light divided by the wavelength. Since this is a constant, its value is 3 into 10 to the power 8 meter per second. So we can write frequency is inversely proportional to the wavelength. So if the wavelength is more, the frequency is less. If the frequency is less, the wavelength is more. It can be understood like this. So if you have a wave like this, so that you can clearly see the wavelength is less, so the frequency is more. That means more waves are there. Here, if we compare here, one wave from this point to this point. So its wavelength is more, its wavelength is less. So alternatively, its frequency is more, its frequency is less. Fine. We can also define one more term here, that is this 1 by lambda. So 1 by lambda, it's also called as wave number. So this is called as a wave number. So the wave number can be written as, since wavelength is centimeters, it can be written as centimeter inverse. So the wave number, the unit of wave number is centimeter inverse. The unit of frequency, that is cycles per second. So that's hertz. That is hertz or cycles per second. So fine. That is hertz or cycles per second, or cycles per second. So that's the unit of frequency, hertz, the number of cycles per second. So the wave number, it is centimeter inverse, and wavelength, it is centimeter. So these are the basics about the units. These are the basic terms which we used in the wave. Is fine. So from this formula we can also write this formula as, so your, not here, you can write here. So your frequency is equivalent as C wave number. So your frequency can be correlated with C and wave number, or it's called C by lambda. So this way also we can write it down. So these are the basic terms you can remember, that the frequency is inversely related to the wavelength, or we can say this, so if wavelength is more, frequency is less. So the frequency basically means the energy. Fine. So we can also write 1 by lambda is equal to wave number, unit to centimeter inverse. Fine. So this is one theory, the basics of the wave theory. Then there is second theory called as quantum theory of electromagnetic radiation. Second. So this was the wave theory. This was all about the wave theory. So we'll go to the quantum theory of electromagnetic radiation. Quantum theory of electromagnetic radiation. The second theory, that is quantum theory of electromagnetic radiation. Quantum theory of electromagnetic radiations, EM. Quantum theory of electromagnetic radiations. So what this quantum theory says, just I'm trying to summarize it. So as per quantum theory, electromagnetic radiation, so electromagnetic radiation, they're consisting of a stream of energy packets. So electromagnetic radiation, basically, a stream of packets, a stream of energy packets, stream of energy packets, or we also call them as quantas. Quantas. So as per the quantum theory of electromagnetic radiation basically exists as in the form of quantas or energy packets. Fine. So these are called as photons. They can be called as photons. This is called as photons. Fine. And the energy associated with each photon, that is equivalent to h nu. Is very important. Energy associated with each packet is equivalent to h nu. H is the Planck's constant. Fine. And nu is the frequency. The value of h we know, that is 6.625 Joule second. Fine. So the value of Planck's constant on the name of Max Planck, scientist. Fine. So this is the, and then we can write energy also, H. So you can convert this frequency nu is equal to C lambda. So that can be called as Hc wavelength. So energy is, you can write this energy of the packet can be written as Planck's constant multiplied with the velocity of light and the wave number. This way also we can write. So this is the electromagnetic radiation in general. So electromagnetic, this again you can look here. Quantum theory of radiation. As per quantum theory, electromagnetic radiation exists in the form of discrete packets or contrasted photons. Energy of each photon is given by h multiplied with the frequency, or we can also write it the hc and then the wave number. Fine, hc nu bar. So this is all about the basics of the wave. Now I'll go back to this now, this spectroscopy. As we mentioned that in the spectroscopy there's interaction of electromagnetic radiation with the matter, and that interaction leads to the transitions in the molecule. Fine. So again we'll write here, the spectroscopy is basically the interaction of, this is a radiation, electromagnetic radiation with the matter. Fine. And then it leads to the transitions in the molecule, the transitions from ground state to the excited state. Now here are two important, the first thing is that so we're using the electromagnetic radiation, fine, and we have matter here and then it leads to transitions. So we have to remember here that which type of transition will occur in the molecule, that depends on the type of radiation we are using, or I can say the type of radiation molecule absorbs. Accordingly there will be the transition. For example, if we use the low energy radiation, so there will be the transition which is the transitions which are of lower energy. Finally, if we use high radiations, so we can get the transitions, so it can alter the transitions, or it can lead to those excitations that are highly energetic. Fine. Or in some of the cases when we use high frequency radiation like X-rays, so it can lead to the ejection of electrons. It can lead to the ionization also. So then it becomes like the photoionization kind of a concept. So we'll sum up like this. So the interaction of electromagnetic radiation with the matter, it leads to the excitation, whether it is electronic excitation, whether it is rotational excitation, whether it's vibrational excitation. That we'll see later. So which type of radiation we'll use and which type of transition will occur, that will sum up here. So we'll sum up in the form of a table here. For example, if we use before we go to this, we'll write the different types of radiations. We'll start from radio waves, then we can go to the microwaves, then we can go to the infrared radiations. I will write IR, infrared radiations, then ultraviolet, visible, so we'll write like this, visible radiations, ultraviolet, so then X-rays. So these are the basics as per our syllabus. We have cosmic rays also and so on, but this is actually which we need. So we can see here. So radio waves, then microwaves, then IR radiations, visible, ultraviolet and X-rays. Now I have arranged them in increasing order of energy. I can see the increasing order of frequency. So they have been arranged in increasing order of energy or increasing order of frequency. Because as we know, energy is equivalent to H in nu. So energy is basically the frequency, right? If you remove this Planck's constant, so mean to say the frequency, that's called the energy. So the radio waves have the low energy, followed by microwaves, followed by IR radiations, then visible, then ultraviolet, then X-rays. Now, since we know frequency is inversely related to the wavelength, so I can write inversely. So if I start from here, so this has less wavelength, followed by this, followed by this, followed by this, followed by this. So that means the radio waves, they have high wavelength, fine, followed by microwaves. So this arrangement of different electromagnetic radiations in increasing order of wavelength or decreasing order of frequency, or increasing order of frequency and decreasing order of wavelength, this is called as electromagnetic spectrum. Electromagnetic spectrum. Electromagnetic spectrum. So electromagnetic spectrum is basically the the order of various electromagnetic radiations in increasing order of wavelength or increasing order of frequency and vice versa, right? Now, so as I was telling earlier, that which type of radiation we use, accordingly there will be a transition in the molecule. For example, we have radio waves, we have microwaves, we have IR radiation. So if we irradiate our sample with, so if we irradiate our sample with radio waves, it has a different impact on the molecule. For example, it leads to the nuclear transitions. Likely if you use microwaves, it leads to the rotational transitions in the molecule. If we have IR radiations, it leads to the vibrational changes in the molecule. If you use visible and ultraviolet radiations, it leads to the electronic transitions. If you use X-rays, then it also leads to the electronic transitions and so on, fine. So now this is all about the basics of the electromagnetic spectrum. Now, as I mentioned, that what is the range of frequency or what is the wavelength of radio waves, that's very important. Likely what is the energy of radio waves and what type of transition it leads. So for that we have to make a table and then we can move further. So till then I think this is enough for today, the basics, the introduction of spectroscopy, again the interaction of electromagnetic radiation in the matter and leading to the transition of the molecule. So in case you have any questions or queries, you can contact me here, makndchem@gmail.com, or you can